Now we are going to discuss about various ways to implement syntax-directed definition. Till now, we have learned what is semantic analysis and how a semantic analyzer can be implemented. So, syntax-directed translation is a method for performing semantic analysis. Now, let's see how a syntax-directed definition can be implemented. There are different ways to implement syntax-directed definitions. One is dependency graph, S attributed definitions, L attributed definitions. Dependency graph is a method to represent the association among attribute instances in a particular parse tree. Since, since the previous examples we have seen, syntax-directed definition primarily focuses on the ordering of evaluation of attributes to get the correct result. Dependency graph are the most general technique to evaluate syntax-directed definitions. As a graph represent, in every graph there is some nodes and edges. Here nodes are used for representing the attributes and edges are for representing the relationship among different attributes. That is, in dependency graph shows the interdependencies among attributes. There is a node for each attribute. For example, if there is an edge from C to B, that means for executing B, it replaces the values of C. Just check this example. Here we can see three attributes, val, this one and this one. These are the three nodes in the dependency graph and we can see edges. Here we can see dashed solid arrows and dashed lines. For the sake of explanation, we can consider dotted lines for parse tree and solid lines for dependency graph. Here for executing the value of the parent, we require the values of the children val and this val. We have constructed the dependency graph. Now we have to know how evaluation can be performed in its dependency graph. For that, we are using topological sort. Any topological sort gives a valid ordering of attributes. In topological sort, it means if we have an edge u, v, u has to be evaluated before evaluating v. We can see more information about topological sort in the coming slide. Now we have to clear what is topological sorting. Topological sorting is used for finding an order of vertices in a graph. Consider this graph directed acyclic graph. These are these many vertices. We have to find a topological ordering of these vertices. For that, this UV, if we have an edge UV, this vertex U has to be evaluated or seen before visiting this vertex V. For example, here 0. Before visiting the 0, we have to visit both 5 and 4. There are various topological ordering possible for this grammar. One of the ordering is 5, 4, 2, 3, 1, 0. And many other possible orders are available here. Now we have to see how the dependency graph can be used for SDD to proper evaluation of attributes. Consider this SDD. This SDD is for type declaration and we are considering an example int id1, id2, id3. As this we have done this previous case, first of all we have to construct the parse tree, then we have to traverse. When we have traverse, we are finding the dependency graph. As mentioned before, solid lines represent the dependency graph edges and dashed lines represent edges in the parse tree. Now, this one means integer. From t gets its integer value from here. From here, this dependency is between t and l. Dependency is between t and l. T gives its value to l. So, which has to be evaluated first? This t has to be evaluated first. Now, l gets a value int. Now, dependency is between this l and this l. Now, we can see the arrow here. This one is like this. That means it's this L has to be evaluated before performing the second L. And again this arrow like this L has to be performed before performing this L. Now this value is ID. And in case of add entry ln dot n, that is performed here, while the value of ID along with this inherited attribute is passed into the symbol table. Now we can see another example for dependency graph understanding. For example, real id1, id2, id3. Consider this same SDD for type declaration. This one is the parse-tree. When we traverse parse-tree, we get the values of attributes. Here this graph represent the dependency among attribute. First of all, it gets the value, T gets the value real, and from T, this L takes the value, so that this arrow. Check the direction, it goes from T to L. That means T has to be evaluated first. Here we have traversed the value of T. From this L, we are going to this L, ID. This L get the value from its parent L, that is shown by the arrow 5 to 7, and from here 7 to 9 means this L gets its value from its parent 7. Now S attributed definitions. S attributed definitions are SDDs that use only synthesized attribute. Now we know what is synthesized attribute. Synthesized attribute means its parent takes its values from children. We can, as synthesized here, S gives AB. In which order we can evaluate this parent? Before evaluating this parent, this A and B has to be completed. That means it is performing in bottom to up direction. So we can evaluate this attribute in bottom up order of nodes. Evaluate the attributes by performing post order traversal. S attributed definitions can be implemented using which parsing method? Bottom up parsing technique. In this, when we have to evaluate the semantic actions once we have seen all the children. That means when reduction happens, then we can perform the semantic action. So we can give the semantic rule at the rightmost end of RHS. That means S gives AB. Semantic curly brace are used to represent the semantic actions are included in the curly brace. This one is valid, but here semantic action is included in between A and B. This is wrong. L attributed definition. L attributed definition can use both synthesized and inherited attribute. As the name L represents, this the attribute can inherit only from its left sibling and parent. A syntax-directed definition is L attributed if every inherited attribute xj, that means xj can inherit only from here. It cannot inherit from this, side. That means Sj can inherit only from its left siblings and parent and cannot from its right siblings. And Sj can inherit value from parent. Here semantic action can be included. Semantic action can be included anywhere on RHS. That means consider this production. S gives A, this one is valid, and this one also valid here. Attributes are evaluated by traversing depth first, left to right. Any S attributed grammars is also L attributed